Imagine a star being stretched like taffy by an invisible force, its light bending into a cosmic spiral as it's torn apart by a black hole's gravity, until suddenly, the sky erupts in a blinding flash of energy, brighter than all the stars in our galaxy combined. This is what NASA's AI detected recently: a black hole in the distant universe devouring a star, its immense gravity ripping the celestial object apart in a violent dance of light and radiation. The event, called a tidal disruption flare, is so rare it's only been observed a handful of times before. But this time, machine learning algorithms flagged the anomaly in a sea of cosmic data, revealing a phenomenon that defies our understanding of how black holes interact with their surroundings. What began as a faint signal in the universe's static became a window into the extreme physics of spacetime, where light bends, time warps, and the fabric of reality shudders under the weight of the unknown. In the vast expanse of space, where cosmic forces shape the universe, a rare and dramatic event has been captured by NASA's observatories. A black hole, one of the universe's most enigmatic objects, has been observed devouring a star, a process so intense and fleeting that it's rarely witnessed. What makes this discovery even more groundbreaking is the role of artificial intelligence in detecting it. This event, which unfolded across millions of light-years, has provided astronomers with a rare glimpse into the violent interactions between black holes and their surroundings. Let me take you through what this means and how it reshaped our understanding of these cosmic phenomena. Black holes are regions in space where gravity is so intense that not even light can escape their pull. They form when massive stars collapse under their own gravity, compressing their mass into an incredibly small space. While black holes themselves are invisible, their presence is often revealed by the way they interact with nearby matter. When a star strays too close to a black hole, the gravitational forces can tear it apart in a process known as tidal disruption. This event releases an enormous amount of energy, creating a luminous burst of light that can be detected across the universe. The discovery in question involved a star being consumed by a black hole, but the details of this event are particularly striking. The star, likely a sun-like star, was drawn into the black hole's gravitational grip. As it approached, the black hole's immense gravity stretched the star, creating a phenomenon called spaghettification, where the star is stretched into a long, thin strand of matter. This material then spirals into the black hole, forming a luminous accretion disk. As the star's gas heats up due to friction and the intense gravitational forces, it emits X-rays and other high-energy radiation. These emissions are what allowed astronomers to detect the event in the first place. However, spotting such an event is no simple task. The process of a star being devoured by a black hole is brief and occurs in a specific region of space, making it difficult to observe. Traditional methods of detecting such events rely on telescopes scanning the sky for sudden bursts of light, but the sheer volume of data collected by modern observatories makes this process time-consuming and prone to missing rare occurrences. This is where artificial intelligence steps in. By training machine learning algorithms to recognize patterns in astronomical data, scientists can sift through vast datasets to identify signs of tidal disruption events that might otherwise go unnoticed. In this case, NASA's AI-driven analysis helped uncover the event by analyzing data from telescopes that monitor the sky for transient phenomena. The algorithm was designed to detect sudden increases in X-ray or ultraviolet emissions, which are characteristic of a star being torn apart by a black hole. The AI's ability to process data at a scale far beyond human capacity allowed it to flag this particular event, which would have been nearly impossible to detect using conventional methods alone. This discovery highlights the growing role of AI in astronomy, where it's becoming an essential tool for uncovering the universe's hidden secrets. The significance of this event extends beyond its rarity. Tidal disruption events are relatively uncommon, occurring perhaps once every few thousand years in a single galaxy. This makes them valuable for studying black holes and their interactions with surrounding matter. When a star is consumed by a black hole, the resulting explosion of energy can provide insights into the black hole's mass, spin, and even its environment. For example, the way the star's material is accreted and the resulting radiation can reveal details about the black hole's properties that are otherwise difficult to measure. Additionally, such events can help scientists understand how black holes influence their host galaxies, as the energy released can affect the surrounding interstellar medium. This particular discovery also underscores the power of multi-wavelength astronomy. By combining observations from different parts of the electromagnetic spectrum, such as X-rays, optical light, and radio waves, astronomers can build a more complete picture of these events. The AI's role in this case was to identify the initial signal, but follow-up observations by human researchers were crucial in confirming the nature of the event and analyzing its details. This collaboration between human expertise and machine intelligence represents a new era in astronomical research, where technology and human insight work in tandem to explore the cosmos. Another fascinating aspect of this discovery is the potential for future observations. While tidal disruption events are rare, the use of AI to detect them suggests that there may be many more such events waiting to be discovered. As telescopes become more sensitive and data collection more extensive, AI tools will play an increasingly important role in identifying these phenomena. This could lead to a better understanding of how black holes grow and evolve, as well as how they interact with their environments. For instance, studying these events might shed light on the role of black holes in galaxy formation and the distribution of dark matter in the universe. Moreover, this discovery serves as a reminder of the dynamic and often violent nature of the universe. While black holes are often portrayed as isolated, silent entities, they are, in fact, active participants in the cosmic dance of matter and energy. The process of a star being devoured by a black hole is a testament to the extreme forces at play in the universe, where gravity can tear apart entire stars and release energy equivalent to the entire output of the Sun over millions of years. Such events, though rare, are crucial for understanding the life cycles of stars and the role of black holes in shaping the cosmos. The implications of this discovery also extend to our understanding of extreme physics. The conditions created during a tidal disruption event, where matter is accelerated to near-light speeds and subjected to intense gravitational forces, provide a unique laboratory for testing the limits of our physical theories. These events can help scientists probe the behavior of matter under extreme conditions, offering insights into the nature of spacetime and the fundamental forces that govern the universe. In this way, the study of such phenomena bridges the gap between theoretical physics and observational astronomy, allowing us to test our models against real cosmic events. Finally, this discovery highlights the importance of technological innovation in advancing our understanding of the universe. The use of AI in astronomy is just one example of how cutting-edge tools are enabling scientists to explore the cosmos in ways that were once unimaginable. As we continue to develop more sophisticated algorithms and observational techniques, we can expect to uncover even more rare and extraordinary phenomena. These discoveries not only expand our knowledge of the universe but also inspire new questions, pushing the boundaries of what we think is possible in the realm of space science. In summary, the detection of a black hole devouring a star, made possible by artificial intelligence, is a remarkable achievement that underscores the power of technology in astronomy. It offers a rare opportunity to study the extreme interactions between black holes and their surroundings, shedding light on the nature of these enigmatic objects and their role in the universe. As we continue to refine our tools and methods, we can look forward to uncovering more of the universe's hidden wonders, each discovery bringing us closer to understanding the cosmos and our place within it. In the vast expanse of space, where stars burn and galaxies spin, a cosmic dance unfolded far beyond our reach. A black hole, invisible to the naked eye, was about to consume a star in a cataclysmic event known as a tidal disruption. This rare phenomenon, where a star is torn apart by a black hole's immense gravity, has long been theorized but rarely observed. However, recent discoveries have brought this cosmic spectacle into sharper focus, thanks to a groundbreaking collaboration between NASA, advanced telescopes, and artificial intelligence. Let's journey through the process that led scientists to witness this extraordinary event, uncovering how cutting-edge technology and human ingenuity unlocked the secrets of the universe. The story begins with the detection of a sudden burst of energy, an intense flash of light that rippled across the cosmos. This flash, captured by NASA's Swift Observatory, was unlike anything seen before. The Swift telescope, designed to detect gamma-ray bursts, is a critical tool in the astronomer's arsenal. Its ability to swiftly scan the sky and capture fleeting cosmic events makes it ideal for spotting such rare phenomena. When the signal was first detected, it triggered an alert: a star had been violently disrupted, and the resulting energy release was being observed in real time. But how did scientists confirm this was indeed a black hole devouring a star, rather than some other cosmic occurrence? The answer lies in the data. The Swift Observatory, along with other telescopes like the Chandra X-ray Observatory and the James Webb Space Telescope, began a coordinated effort to gather more information. These instruments, each with its unique capabilities, worked in tandem to paint a fuller picture. The Chandra Telescope, for instance, specializes in X-ray observations, allowing scientists to peer into the high-energy remnants of the disrupted star. Meanwhile, the James Webb Space Telescope, with its infrared capabilities, could detect the faint glow of the star's debris as it spiraled into the black hole. Together, these observatories formed a network of eyes across the cosmos, each contributing a piece of the puzzle. But even with this wealth of data, the challenge remained: how to sift through the vast amounts of information to identify the unique signature of a tidal disruption event. Here, artificial intelligence stepped in. AI, trained on thousands of similar cosmic events, was able to analyze the data at an unprecedented speed. The machine learning models, designed to recognize patterns in light curves and energy emissions, flagged anomalies that human eyes might have missed. These models were not just passive observers, they acted as intelligent assistants, processing petabytes of data and highlighting potential candidates for further investigation. The AI's ability to learn from past observations allowed it to refine its search, narrowing down the possibilities and focusing on the most promising signals. The timeline of this discovery is as remarkable as the event itself. The initial detection by Swift occurred in a matter of seconds, triggering an automated alert system that notified astronomers worldwide. Within hours, teams at NASA and other institutions began analyzing the data, cross-referencing it with historical observations and theoretical models. The next few days were a flurry of activity, as telescopes pointed their lenses at the location of the event, capturing detailed images and spectra. Each observation added another layer to the story, revealing the dynamics of the star's destruction and the behavior of the black hole in its vicinity. One of the key moments in this process was the confirmation of the event's nature. The AI's initial analysis suggested a tidal disruption, but scientists needed to verify this through additional evidence. The Chandra Telescope's X-ray data provided crucial insights. As the star was torn apart, its debris formed an accretion disk around the black hole, emitting intense X-rays. These emissions, detected by Chandra, matched the expected signatures of a tidal disruption event. Meanwhile, the James Webb Space Telescope's infrared observations revealed the lingering glow of the star's remnants, offering further confirmation. The combination of these data points painted a compelling picture: a black hole had indeed devoured a star, and the aftermath was being observed in exquisite detail. The role of AI in this discovery cannot be overstated. Traditional methods of analyzing astronomical data are limited by human capacity and time. AI, however, can process vast datasets in minutes, identifying patterns that might take years for humans to discern. In this case, the AI's ability to recognize the unique light curve of a tidal disruption event was instrumental. The light curve, a graph of the event's brightness over time, showed a distinct pattern: a sudden spike followed by a gradual decline. This pattern, characteristic of a star being consumed by a black hole, was a key clue that led scientists to the correct conclusion. Without AI, such a discovery might have taken far longer, or perhaps never been made at all. The collaboration between AI and human scientists was a defining aspect of this discovery. While the AI provided the initial insights, human experts were essential in interpreting the data and validating the findings. Astronomers meticulously examined the AI's predictions, cross-checking them with theoretical models and historical data. This iterative process ensured that the discovery was not just a product of algorithmic analysis but a result of rigorous scientific inquiry. The AI acted as a powerful tool, amplifying the capabilities of human researchers and enabling them to explore the cosmos in ways previously thought impossible. The implications of this discovery extend beyond the immediate observation. Tidal disruption events are rare, occurring only a few times a century in any given galaxy. By studying these events, scientists gain valuable insights into the behavior of black holes and their role in shaping galaxies. The energy released during such an event can influence the surrounding interstellar medium, triggering star formation or disrupting existing structures. Understanding these processes is crucial for unraveling the life cycles of galaxies and the evolution of the universe itself. The AI-assisted detection of this event has opened new avenues for research, allowing scientists to explore these cosmic phenomena with greater precision and frequency. As the dust settled on this cosmic event, the scientific community reflected on the significance of the discovery. The integration of AI into astronomical research marks a new era in space exploration, where technology and human ingenuity work in harmony to unlock the mysteries of the universe. This discovery is a testament to the power of collaboration between machines and humans, between observatories and algorithms, and between curiosity and the vast, uncharted expanse of space. It is a reminder that even in the darkest corners of the cosmos, where light is scarce and time is measured in millennia, there is always something waiting to be discovered, if only we have the tools and the determination to find it. When a star ventures too close to a black hole, the gravitational forces at play become so intense that they tear the star apart. This dramatic event, known as a tidal disruption, is a cosmic spectacle that releases an enormous amount of energy, enough to outshine entire galaxies for brief periods. The process begins when the star's gravity can no longer withstand the immense pull of the black hole. As the star is stretched and pulled apart, its material forms a swirling disk of gas and dust around the black hole, a phenomenon called an accretion disk. This disk heats up to extreme temperatures, emitting radiation across the electromagnetic spectrum, from X-rays to visible light. These emissions are what allow astronomers to detect such events, even when they occur millions of light-years away. However, the rarity of these occurrences means that spotting them requires both advanced technology and innovative methods. Enter artificial intelligence, which has revolutionized the way scientists search for and analyze these cosmic phenomena. By processing vast amounts of data from telescopes, AI can identify subtle patterns and anomalies that might otherwise go unnoticed, making it possible to study these rare events in greater detail. The recent detection of a black hole devouring a star, facilitated by AI, is not just a remarkable observation, it is a gateway to deeper insights into the fundamental physics of black holes and their role in shaping the universe. Understanding these events is crucial because they provide a unique opportunity to study the extreme conditions near black holes, where the laws of physics are pushed to their limits. The energy released during a tidal disruption event can influence the surrounding interstellar medium, potentially triggering star formation or altering the dynamics of galaxies. Moreover, these events offer a rare glimpse into the behavior of black holes, which are otherwise elusive and difficult to observe. By analyzing the light emitted during such an event, scientists can infer properties of the black hole, such as its mass and spin, and even test theories about gravity in extreme environments. The significance of this discovery extends beyond the immediate observation. It highlights the power of AI in modern astronomy, where the sheer volume of data collected by observatories far exceeds human capacity to process it manually. AI algorithms can sift through this data with remarkable efficiency, identifying potential candidates for further study. This capability is particularly vital for rare events like tidal disruptions, which may occur only once in a galaxy's lifetime. The integration of AI into astronomical research is not just about finding more events, it's about refining our understanding of the universe's most extreme phenomena. For instance, the detection of a tidal disruption event can help scientists validate or challenge existing models of black hole behavior. If the observed data aligns with theoretical predictions, it reinforces our current understanding. If not, it opens the door to new hypotheses and discoveries. This interplay between observation and theory is a cornerstone of scientific progress. Furthermore, the study of tidal disruptions contributes to our broader understanding of galaxy evolution. Black holes, particularly supermassive ones at the centers of galaxies, are thought to play a critical role in regulating star formation and shaping galactic structures. The energy released during a tidal disruption event could influence the surrounding gas and dust, potentially affecting the rate at which new stars form. By studying these events, scientists can piece together how black holes interact with their environments and how these interactions influence the life cycles of galaxies. The implications of such research are far-reaching. They not only deepen our knowledge of black holes but also shed light on the fundamental processes that govern the universe. For example, the study of tidal disruptions can provide insights into the nature of dark matter, as the distribution of matter in galaxies is closely tied to the behavior of black holes. Additionally, these events offer a unique laboratory for testing the predictions of Einstein's theory of general relativity, which describes how gravity behaves in extreme conditions. The extreme gravitational forces near a black hole create a perfect environment to probe the limits of our current physical theories. Any deviations from expected outcomes could hint at new physics beyond the standard model. The detection of a tidal disruption event, therefore, is not just an isolated observation, it is a piece of a much larger puzzle. It connects the study of individual stars to the broader context of galaxy evolution and the fundamental forces that shape the cosmos. The role of AI in this discovery underscores the growing importance of computational methods in astronomy. As telescopes become more sensitive and data collection becomes more extensive, the need for advanced analytical tools will only increase. AI is not replacing human scientists but augmenting their capabilities, allowing them to explore the universe in ways previously unimaginable. This synergy between human ingenuity and machine intelligence is driving a new era of discovery, where the boundaries of our knowledge are continually expanded. The significance of this particular event lies in its rarity and the insights it provides. While tidal disruption events are not uncommon in the universe, they are difficult to detect due to their fleeting nature and the vast distances involved. The use of AI to identify such an event demonstrates the potential of these technologies to uncover hidden aspects of the cosmos. It also highlights the importance of interdisciplinary collaboration, as the success of this detection relied on advancements in both observational astronomy and machine learning. As we continue to refine our tools and techniques, the prospect of discovering more such events becomes increasingly promising. Each new observation contributes to a more comprehensive understanding of the universe, revealing the intricate dance between stars, black holes, and the forces that govern their interactions. In the end, the study of tidal disruptions is more than just an exploration of extreme cosmic phenomena. It is a testament to humanity's ability to seek answers to the most profound questions about our place in the universe. By unraveling the mysteries of black holes and their interactions with stars, we gain a deeper appreciation of the cosmic forces that have shaped the universe and continue to influence its evolution. The detection of this rare event, made possible by AI, is a reminder that the universe is full of wonders waiting to be discovered and that the tools we develop today will shape the next chapter of our cosmic exploration. NASA detects rare phenomenon of a black hole devouring a star with help of AI. ABC News. This part of our deep dive into NASA detects rare phenomenon of a black hole devouring a star with help of AI. ABC News focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The discovery of a black hole devouring a star, detected through the power of artificial intelligence, has opened a window into one of the universe's most violent phenomena. Yet, even as scientists marvel at the precision of this observation, a host of open questions remain. How exactly does a black hole tear apart a star? What happens to the material after the destruction? And how common are these events in the cosmos? These mysteries form the heart of the scientific debate, challenging researchers to refine their models and rethink the dynamics of stellar interactions with these cosmic giants. The event, observed through telescopes and analyzed by AI, has provided a rare glimpse into the chaotic dance between a star and a black hole, but the data still holds secrets that demand further exploration. For instance, while the initial detection was dramatic, a sudden flare of light as the star was consumed, the details of the process remain elusive. The AI's ability to spot such an event was groundbreaking, but it also raises questions about the reliability of machine learning in identifying rare cosmic phenomena. Could there be false positives, or is this truly a one-in-a-million occurrence? Moreover, the physics of tidal disruption events, where a star is stretched and torn apart by a black hole's gravity, is still not fully understood. Some models predict a slow, gradual disintegration, while others suggest a more explosive, sudden collapse. The observed light curve from this event, which showed a rapid rise and fall in brightness, hints at a complex interplay of forces, but the exact mechanisms at play are still under scrutiny. Scientists are also grappling with the aftermath of the destruction. Once the star is shredded, the debris forms a disk of gas and dust around the black hole, emitting intense radiation. However, the energy released during this process is staggering, equivalent to the sun's output over millions of years. Yet, the precise distribution of this energy and its impact on the surrounding environment remain unclear. Are these events rare, or are they more common than previously thought? The AI's role in detecting this particular event suggests that such occurrences may be more frequent than earlier estimates, but the lack of similar observations in the past could indicate that this is an exceptional case. Additionally, the nature of the black hole itself is a point of contention. Was it a supermassive black hole, millions or billions of times the Sun's mass, or a smaller stellar mass black hole? The answer could influence our understanding of how these objects interact with stars in different galactic environments. Finally, the broader implications of this discovery extend beyond the immediate event. If black holes are more actively consuming stars than previously believed, it could reshape our models of galaxy evolution and the role of supermassive black holes in shaping their host galaxies. Yet, for all the insights gained, the mystery of how a black hole devours a star and what happens afterward remains a compelling enigma, driving scientists to push the boundaries of observation and theory. As we look to the future, the tools and missions that have already begun to shape our understanding of these cosmic events are set to evolve, offering even deeper insights into the mechanics of black hole-star interactions. The discovery of a black hole devouring a star, aided by artificial intelligence, has already demonstrated the power of machine learning in detecting rare and fleeting cosmic phenomena. But this is just the beginning. Future missions and instruments, both in space and on Earth, are poised to expand our observational capabilities, refine our models, and perhaps even challenge existing theories about how these violent processes unfold. Let's explore what lies ahead in this exciting frontier of astrophysics. One of the most immediate next steps in this field is the continued refinement of AI-driven analysis techniques. The algorithms that helped identify this event are already being trained on larger datasets, incorporating data from past observations and simulations. These enhanced models could detect subtle patterns in light curves, flashes of light emitted as a star is torn apart by a black hole, that were previously overlooked. For instance, the light from such an event might exhibit unique spectral signatures as the star's material heats up and emits radiation. By analyzing these signals with greater precision, AI could not only confirm the occurrence of similar events but also reveal details about the black hole's mass, spin, and the dynamics of the accretion disk. This would allow scientists to test theoretical predictions about how black holes interact with their surroundings, potentially uncovering new physics. Meanwhile, the James Webb Space Telescope, JWST, launched in 2021, is already revolutionizing our ability to study distant cosmic phenomena. While its primary mission focuses on the early universe and exoplanet atmospheres, JWST's advanced infrared instruments could provide critical data on these star-black hole encounters. The telescope's ability to peer through dust clouds and observe faint, distant objects makes it uniquely suited to study the aftermath of such events. For example, the light from a disrupted star might be obscured by interstellar material, but JWST's sensitivity could allow astronomers to detect it. Additionally, the telescope's high-resolution spectroscopy could analyze the chemical composition of the ejected material, offering clues about the star's composition and the conditions in the black hole's vicinity. These observations would complement the optical data collected by ground-based telescopes, painting a more complete picture of the event. Another key player in the future of this research is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This telescope, a successor to the Hubble, will be equipped with a wide-field camera capable of surveying vast swaths of the sky. Its primary mission is to map dark energy, but its observational power could also make it an invaluable tool for detecting transient events like black hole star collisions. The Roman telescope's ability to monitor large areas of the sky continuously means it could capture the brief, luminous flashes associated with these phenomena. By combining data from Roman with that from other observatories, scientists could track the evolution of these events in real time, from the initial tidal disruption to the eventual disappearance of the star's light. This would provide a dynamic, multi-stage view of the process, something that has been challenging to achieve with current instruments. On the ground, the Vera C. Rubin Observatory in Chile, scheduled to begin operations in the early 2030s, represents another leap forward. Its Legacy Survey of Space and Time (LSST) will conduct an unprecedented survey of the southern sky, capturing billions of galaxies, stars, and transient events over a decade. The observatory's wide-field camera, with its ability to detect faint objects and track changes over time, could identify new instances of tidal disruption events. By comparing images taken years apart, astronomers could spot the telltale signs of a star being consumed by a black hole. The Rubin Observatory's data will also be invaluable for studying the distribution of such events across the universe, helping to determine whether they are rare anomalies or more common occurrences that have been undercounted in the past. Beyond individual missions, the field of multi-messenger astronomy is set to play an increasingly important role. This approach combines observations from different types of signals such as electromagnetic waves, gravitational waves, and neutrinos to study cosmic events from multiple perspectives. The recent detection of gravitational waves from black hole mergers by the LIGO and Virgo collaborations has already provided groundbreaking insights into the nature of these objects. While the event we've discussed here involves a black hole interacting with a star rather than merging with another black hole, future gravitational wave detectors could still contribute. For example, if the tidal disruption event generates detectable ripples in spacetime, a space-based observatory like the Laser Interferometer Space Antenna, LISA, planned for the 2030s, might capture these signals. Combining gravitational wave data with optical or X-ray observations could reveal new details about the black hole's properties and the energy released during the process. However, the path forward is not without challenges. One of the biggest hurdles is the rarity of these events. A black hole devouring a star is an extremely rare occurrence, and even with advanced instruments, it may take years to observe another instance. This scarcity means that each detection is a precious data point, requiring meticulous analysis to ensure accuracy. Additionally, distinguishing these events from other phenomena, such as supernovae or gamma-ray bursts, requires sophisticated modeling and cross-referencing with theoretical predictions. Future missions must therefore prioritize both sensitivity and specificity, ensuring that observed events are correctly identified and classified. Another area of uncertainty lies in the exact mechanisms of tidal disruption. While current models suggest that a black hole's immense gravity stretches a star into a long, luminous stream before it is consumed, there are still gaps in our understanding. For example, the role of magnetic fields in shaping the ejected material or the impact of the black hole's spin on the event's dynamics remain topics of debate. Future observations could address these questions by measuring the geometry of the accretion disk, the velocity of ejected material, or the presence of relativistic jets, high-energy streams of particles that some black holes emit. These measurements would not only refine existing theories but also open the door to new hypotheses about how black holes interact with their environments. The importance of these future observations extends beyond the study of black holes themselves. By understanding how these cosmic giants consume stars, we gain insight into the broader processes that shape galaxies. Black holes are thought to play a crucial role in regulating star formation and influencing the evolution of galaxies through feedback mechanisms. Observing tidal disruption events could therefore provide a window into these processes, helping us piece together the complex interplay between black holes and their host galaxies. Moreover, studying these events could shed light on the distribution of dark matter, as some models suggest that dark matter halos might influence the dynamics of tidal disruption. As we look ahead, the collaboration between cutting-edge technology and human ingenuity will be key to unlocking the mysteries of these cosmic phenomena. The development of next-generation instruments, the refinement of machine learning algorithms, and the expansion of multi-messenger astronomy all point to a future where such events are not just detected but fully understood. Each new observation brings us closer to answering fundamental questions about the universe's most extreme environments. And while the rarity of these events means that each discovery is a rare gem, the collective effort of scientists and engineers ensures that we are well equipped to find more and to explore even deeper into the cosmos. NASA detects rare phenomenon of a black hole devouring a star with help of AI. ABC News. This part of our deep dive into NASA detects rare phenomenon of a black hole devouring a star with help of AI. ABC News focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.